Have you ever felt like you're putting in a ton of effort, but not really getting anywhere? Well, in physics, that's not just a feeling, it's a measurable fact. So today, we're going to talk about vector projections, which is basically the math that lets us find the useful part of any effort and separate it from the energy you just, well, waste. Let's see how it's done. To really wrap our heads around this, we're not going to start with some dry formula. Nope, we're going to start with a problem that I bet you've experienced yourself. You know when you're pushing a lawnmower, you're pushing down on the handle and you're pushing forward. But think about it. That downward push doesn't actually help the mower move forward one bit. It's just wasted effort, literally pushing the wheels into the grass. So the big question is, how can we figure out exactly how much of your force is doing the useful work and how much is just wasted? Okay, so here's the core idea. The force you're applying is a vector. It's got a direction and a strength. But when you apply that force at an angle, it kind of splits into two parts. You've got the horizontal part, which is what actually moves the mower forward, and then you have the vertical part, which is just pushing it down. Projections are the tool we use to find that one useful horizontal piece. You know, the best way to visualize a projection is to just think of it as a shadow. Seriously, imagine the sun is directly above one vector. The shadow it casts on another vector below it, that's the projection. It's the piece of the first vector that lies perfectly along the second one. So how do we actually measure this shadow? Well, we have two different tools to do it. There's something called the scalar projection, which tells us how long the shadow is, and then there's the vector projection, which describes the shadow itself as its own vector. One gives you a length, the other gives you the actual thing. Let's look at why you need both. First up is the scalar projection. People often write it as comp for component. It answers one simple question. How long is the shadow? That's it. It's just a number, a magnitude. Now, if the shadow points in the same direction as the vector it's on, that number is positive. But if it points in the opposite direction, it's negative. It gives us the length, but that's all. And then you've got the vector projection, or proj. Now, this isn't just a number. This is the shadow. It's a full-on vector, with its own magnitude and its own direction. This represents the actual, useful part of our force that is working in the direction we want to go. All right, that's enough theory. Theory's great, but the best way to really get this stuff is to see the formulas in action. So let's walk through a few examples together. Let's start with this straight-up math example, no physics yet. We want to project vector u onto vector v. So step one, we need to calculate two things. The dot product of our vectors, u and v, and the magnitude or length of v. Now the scalar projection, the length of our shadow, is just the dot product divided by the magnitude of the vector we're projecting onto. So 15 divided by 5 gives us 3. That's the length. Then to get the actual vector projection, we basically just use that length to scale a unit vector of v. That gives us our final answer, the vector 3, 0. Okay, back to physics. Imagine you have a force, let's say the vector 4, 3 newtons, and it's being used to move an object. But the object only moves horizontally for 10 meters, so its displacement is 10, 0. The question is, how much work is actually done here? Just remember, in physics, work is the dot product of force and displacement. And the answer is 40 joules. But the really cool part is why. When we take the dot product of the force 4, 3, and the displacement 10, 0, what do? We do 4 times 10 plus 3 times 0. See that? That vertical part of the force, the 3 newtons, gets multiplied by 0 because there was no vertical motion. The dot product automatically isolates only the part of the force that's in the same direction as the motion. It's perfect. Okay, here's our most realistic example yet. You're pulling a wagon. You're using 50 pounds of force, and you're pulling at a 30-degree angle. So how much of that 50 pounds is actually helping to pull the wagon forward? Well, first we use a little basic trigonometry to turn that into x and y components. The horizontal part is 50 times cosine of 30, and the vertical is 50 times sine. Once we have that force vector, we just need to find its scalar projection in the horizontal direction. And boom, there it is. Of the 50 pounds of force you're exerting, only about 43.3 pounds is actually effective at pulling that wagon forward. The rest of that effort, it's just lifting the handle up, which isn't helping you move forward at all. All right, so we've seen how to do it right. Now let's talk for a minute about how to not do it. There are a few classic mistakes that are super easy to fall into, but they're just as easy to avoid once you know what you're looking for. First, and this is a big one, mixing up scalar and vector projections. If a question asks for a vector and you give a single number, you've missed the whole point. Second, Watch your subscripts. Projecting U onto V is totally different from projecting V onto U. You get two completely different shadows. And finally, a classic for any physics problem, don't forget your units. Force in newtons times distance in meters gives you work in joules. Always remember the units.
So after all this math, after all these examples, what's the big takeaway? Well, it all comes down to a really simple but kind of profound idea about what work actually is. This is it. This is the mind-bending but absolutely essential idea from physics. If your force is perfectly perpendicular at a 90-degree angle to the direction something is moving, you are doing zero work. Think about holding a heavy box and walking forward. You're exerting force upwards to hold the box, but the motion is forward. Your upward force does zero work in the forward direction. You get tired for sure, but by the physics definition, the work is zero. The dot product reveals this incredible truth.
And that brings us to the final thought here. This whole idea of splitting effort into a useful part and a wasted part isn't just for lawnmowers and wagons. It's used in computer graphics to literally create shadows. It's used in machine learning and all over engineering. So I'll leave you with this question. Now that you understand the math behind it, where else in your world is getting something done just a matter of making sure your vectors are lined up?